All right, good afternoon, everyone. Thank you for having me. Thank you for choosing the session. My name is Salman. I'm excited to be here to talk to you about some neat things that we've been working on around garbage collection technology. So today, specifically, we'll be talking about adaptive GC threading, a cool solution to a problem that I like to call the Goldilocks dilemma with GC parallelism. So I'll just take a step back for those who are unfamiliar with Goldilocks, the Goldilocks principle. It's an analogy with origins in a children's book about a girl who tastes bowls of porridge left back by three bears. And as she's tasting each bowl, she realizes one is too hot, the other is too cold, and there's one that's just right, just the right temperature. So we'll be kind of exploring this idea with GC parallelism, this idea of too many threads or not enough threads. And we'll talk about why there's even a question, the challenges around it, and some of the things that we've kind of done to address those. So just a little bit about me before we begin. I'm a software developer on the IBM's runtimes technology team, specifically the VMGC team. I've been working on garbage collection technology for just over 4 years now, worked various areas and issues around garbage collection. But mainly my focus and my interest has been in performance. So it's my first time here in Germany, first time at EclipseCon, and first presentation at a conference. So I'm here today from Canada. I'm from Ottawa. I was born and raised in Ottawa and graduated from the University of Ottawa. And that's where you'll actually find most of us folks from IBM on the VMGC based out of Ottawa from. All right, so the agenda for today, we'll start off with a brief overview of garbage collection. I assume everyone has some sort of idea, but I'll throw a slide or two up just to get everyone up to speed. Then we'll look at GC technology and how it's designed to accommodate various use cases and how it's designed to make trade-offs. And then we'll take a deep dive into performance and optimizations. And then we'll zero in onto GC parallelism and talk about what it means to garbage collection tasks. And then we'll see how the Goldilocks dilemma emerges. And that really showcase how this need for adaptive threading came about. And so we'll talk about the core idea behind it, some implementation details, and then we'll finish things off with some performance results. So all the work that I'll discuss today is available online for anyone to take a look at, as developed in the open across two Eclipse projects, Eclipse OMR and Eclipse OpenJ9. So just a quick shout out to those projects. OMR is a project that provides a set of components to build language runtimes. And OpenJ9, as some of you may be aware, is an independent implementation of the JVM. So I welcome everyone to take a look at these projects if some of these things interest you. So both of these projects are important to us at IBM. They're built and combined with Java class libraries from OpenJDK by IBM to build the IBM Samu Runtimes Java build, which strives to optimize for cloud-native applications. So this build is published online for anyone to download, try out, and maybe use in production at no cost. All right, so we're here to talk about garbage collection, or GC for short. As many of you may already know, garbage collection is simply or fundamentally just a form of automatic memory management with the end goal of reclaiming memory that's no longer required by a program. So this memory is what we refer to as garbage, hence garbage collection. So nowadays, a large majority of languages do provide some sort of automatic memory management. If you look at the top 10, top 20 languages, the majority of them have some sort of automatic memory management component to them. So I don't think we need to make a case for it. It eliminates a large category of bugs, speeds up development, lets the developer focus on the problem at hand, et cetera, et cetera. But without a doubt, there are some costs and drawbacks associated with this. Simply put, managing the heap is not free. So first, I think it's important to understand that GC implies a lot more than just reclaiming memory. It's true that at the core of it, it's about finding live objects and then reclaiming the memory that's no longer needed. But in order to do that, it needs to take care of a few things. It needs to handle the allocations themselves. It needs to manage the memory layout, the heap, and it needs to ensure validity of objects, make sure objects pass through the correct access barriers on mutations. So all that to say, GC touches a lot of different runtime components. So anyone looking at application performance has to consider the implications of GC. GC is usually seen as a black box, but I think it would be helpful and useful for anyone to kind of understand the inner workings to see how issues can arise from within and ultimately affect the application. So more practically, this is kind of like an illustration of a GC relative to the application. Over here, we have an application running. It's doing some useful work. Application threads are allocating objects. And at some point, there's not enough memory. So there's an allocation failure. And so the GC has to kick in. And so this is where things get interesting. For the GC to kick in, it needs to acquire exclusive VM access. And what that does is that it causes a stop-the-world operation. And so there's this timing goal for the application when it's completely halted. So we could refer to this as a GC cycle, GC pause, application pause. So these are just kind of different words to kind of refer to the same thing. So since there is an application pause, the length of each pause and the amount of times we have to pause are clearly significant for the application. So a lot can be said here, but I think for the purposes of this talk, I just want you guys to keep this in mind as we move forward. So anyone that works on the GC or the JVM has been at least asked once or been asked over thousands of times, the same question, the same major concerns and complaints around GC pauses. My GCs are too long, they interfere with my application doesn't respond fast enough. What can I do about it? And for that, the biggest problem is that I always tell people it's like a knob. It's always a trade-off between GC pauses and application throughput. And for the most part, nobody really likes to hear about giving up on application throughput, but they also don't like the GC pauses. Certainly, it would be great to kind of optimize for all metrics and maximize performance in all situations. But GC technology is designed to make trade-offs to support various use cases. Under the hood, as GC developers, we design the collectors to make sure the trade-offs are done as optimally as possible so that performance is maximized as much as possible from every aspect. So just because we're optimizing for pause times and we might give up on some throughput, we still care about throughput. It's just that the priority might be different to accommodate a different use case. So what it boils down to at the end of the day for the user is a compromise between three main things: the application throughput, the latency or GC pauses, and sometimes footprint. And these can be significant and considerable. Let's just take a look at footprint for a second. If you have thousands of VMs deployed to the cloud and they're built based on memory consumption, then the application's footprint is going to be significant and considerable. And GC is going to have a large part to play in that. And so what that means for us, GC developers, is that the internal technology that we develop to accommodate these various use cases and goals is significantly different. So for example, we can have different heap configurations, different allocation patterns, different styles of collection. But I think the most evident is when we consider the stop-the-world technology versus concurrent technology. With stop-the-world, you're maximizing the throughput, but you're getting longer pauses. With concurrent, you're giving up on some throughput as the GC runs concurrently with the application, but you're minimizing pause time. So it's these trade-offs. So the goal is not to eliminate overhead, but that's a given, right? But the key is to have justified and tolerable GC behavior in all situations. And that's the tricky part. Although there are general rules and patterns how the GC should behave, but no two machines, no two workloads, no two applications are the same or have the same characteristics. But the GC should be able to handle any context with predictable overhead or tolerable overhead. Be it big data and 1 terabyte heaps or a memory constrained environment just with a few megabytes. So when we're outside of a tolerable range or have unjustified behavior, the GC should be smart enough to detect these scenarios and adjust for them. So it should be able to tune internal parameters to kind of fit the context. And it's not a question of if it needs to be, it's just a question of when, because GC will always be running in different contexts and will need to self-adjust. And that's essentially why a large category of optimizations, GC optimizations, are needed. So let's look at one example, and let's consider dynamic heap resizing. With dynamic heap resizing, we're constantly expanding and contracting the heap to kind of make a trade-off with overhead. So when we realize that the interval between GC cycles is too high, or GC overhead is too high, we can expand the heap, give up on some footprint, and try to minimize that overhead. Or we can completely ignore footprint, fully expand the heap, and to make sure that overhead is minimal in all situations, especially during startup when the heap is constantly being adjusted. So now we'll explore these ideas a bit more concretely by taking a look at GC parallelism. We'll see how inefficient parallelism leads to unnecessary overhead and ultimately results in longer than necessary pause times. Through this, the Goldilocks dilemma with parallelism, GC parallelism will emerge, and we'll see how it's necessary to find that sweet spot, that's just right, with multi-threading to maximize GC performance. So let's break down the GC cycle and take a look at what the multi-threading activity looks like. So we expect to see 3 distinct phases. Once, as GC kicks in, there's one single main GC thread running that's doing setup, that's getting ready to start the collection, and then parallelism kicks in. multiple threads and workers are dispatched. They work in parallel. They do bulk of the collection work. They finish up, and then the main GC thread cleans up, does some bookkeeping, and returns control back to the application. So the optimization of adaptive threading came about when looking at this parallel activity from using multiple GC threads and seeing their effects on pause times. So the question is, like, how many threads should we be using? And the naive common assumption is use as many as possible that the hardware allows to kind of use all the resources and speed up processing times. But as we'll see in a bit, this is not always true, and in fact can be a harmful assumption. So what does parallelism mean, and what does it mean to the GC specifically? I think parallelism or multi-threading is a given with any modern computing system that's CPU-intensive, computational-heavy processing work, especially in the last 2 decades with how computing has evolved. Throughout the years, computing hardware has been increasingly scaled with multi-core processors, so there are more resources available for applications to take advantage of. And naturally, GC tasks are parallelized to speed up processing times and overall become more performant. So for example, if you consider walking the heap or walking the object graph, looking for live objects with 2 threads versus single-threaded, we'd expect with 2 threads we could process twice the amount of work. We could process the same amount of work in half the time, because we could do twice the work in the same unit of time. So all that to say, with parallelism, we expect pause times to be reduced as we have more resources available and speed up cycle times and reduce pause times. So this is nothing new. All collectors in all major VMs are parallelized to utilize available resources. So for example, in OpenJ9, when we set up the VM, when we set up the GC, the number of application level threads we set up for the GC is equal to the number of hardware threads that we query from the OS. So you're probably wondering, what's the issue? What's the big deal? Everything looks okay. If you have more resources, we should be able to use them, right? But let's take a look at this example, which tells a bit of a different story. Over here, we have the pause times plotted as an application runs, so GC pauses. We have 2 runs plotted here. They're of the same application, running on the same machine. It's a 48-core machine. It's a pretty large machine with 48 hardware threads available. The only difference between the 2 runs is in one run, we're limiting and forcing parallelism to 4 threads. In the other, we're letting it use all the available hardware resources, which is 48 threads. So there's something clearly wrong here. Pause times are 3 to 4 times consistently higher when more threads are used. And so that doesn't quite follow some of the things that I've been saying. We're seeing that as we increase parallelism, we're getting longer pause times. So running with 4 threads is like equivalent to running on a smaller machine with less resources. And intuitively, a larger machine should perform better than a smaller one, right? Or it should perform at least the same. You shouldn't be penalized for using a larger system. That just doesn't make any sense. But on the larger machine, we can make out that there are some unjustifiably long collection times. And given that the only varying parameter between the 2 runs is the number of threads, we can confidently say that parallelism is detrimental on this large machine. So we have to ask ourselves and look at whether there are any costs to parallelism. We do know that there are additional requirements when it comes to multi-threading. We have to synchronize. So there's critical sections. Threads are accessing global resources. There could be races between threads. And then threads also have to be managed, right? So if you look more into it, we quickly realize that this is prevalent across all GC operations. GC is basically designed with a parallel model, programming model. There's lots of locked operations and places where we can have contention on shared memory. And just one example of that is a mark map. It's a very important structure for the GC, which keeps track of live objects. And a single mark bit in the mark map might correspond to multiple objects. So we can have a race between threads as they're accessing the mark map, so there could be contention there. So it has to be a locked operation. Another example is GC threads are very frequently pushing and popping onto work stacks or in-queuing and de-queuing onto queues. And so the issue there is that we can have some idle threads that are waiting for work. They don't have anything to do. We have producer threads, which are producing work. And once they have enough work to share, they need to kind of push it to the work stack and then notify the idle threads. So pushing onto the work stack has to be done in kind of a synchronized way. And then notifying the idle threads is also like a bit of an overhead. And as threads are waking up, they could have a race to kind of access that work. So these are all things to consider when we speak about synchronization of GC threads. Of course, there could have little optimizations here, like split lists and whatnot. But overall, there's an issue. So how can we explain this, and how can we reconcile with this detrimental parallelism? Well, at the root of it, for this to happen, the cost of the overhead from parallelism has to be greater than any of the benefits that it provides. So we have to kind of look at which GC scenarios essentially result in threads being a net loss or threads being useless. For that, we can consider two cases, which are quite intuitive. So one, when there's actually nothing for the threads to do, so they're just waiting there idle. And that can be because there's an imbalanced workload distribution. So it's possible, given the object graph, we can't actually divide up the work past a certain number of threads. So when we use too many threads, threads are essentially useless. Or we can simply not have enough work at all, right? There's just not that much work to go around. And so in these cases, threads are left idle and unused, but they still go through the steps of GC. They still have to be managed. They still have to reach synchronization points. So we incur overhead without gaining many benefits. And the second case is with high CPU saturation or high CPU load. In this case, hardware resources are shared amongst different processes, different VMs. As a thought experiment, we can imagine two VMs running at the exact same time, doing GC at the exact same time. And if both GCs are trying to optimistically use all the hardware resources, then there could be an issue as they're split between the two GCs, so progression is being limited as the hardware resources are being shared. And so there's also cost to context switching as well there. But what I do want to stress is for the GC, in ideal situations, and the key is ideal, parallelism provides significantly more performance benefits than overhead. And we can basically say that overhead is negligible and we don't really need to worry about it. But as mentioned at the beginning of the talk, GC should be ready and smart enough to handle any situation with any configuration and any workload. So in these cases that lead to inefficient parallelism, GC is not quite doing something right there. And this overhead can be significant as it increases proportionally with the number of threads that we use. Each extra thread is just dead weight, incurring overhead without providing many benefits. So this kind of reminds me of an analogy that you might be all familiar with, which is basically too many cooks in the kitchen, which says that if there's too many people or too many resources on working on something, it can negatively affect the end product. Like with too many cooks in the kitchen, everyone has their own idea. There's not enough space. There's not enough work for them to do. And so that's precisely, you can say, kind of like what's happening with these threads when the situation is not conducive for many threads. So knowing this, we have to ask ourselves, like, what's the right number of threads to maximize efficiency without creating that chaos that's like in the kitchen? Are we using too many threads and getting detrimental effects? Or if so, how much should we decrease by? And if we decrease, is it possible that we're missing out on opportunities to further gain benefits by parallelizing the task? So it's like the Goldilocks example, where Goldilocks is tasting each bowl of porridge, realizing one is too hot, the other is too cold, and she's kind of tasting the different bowls to figure out the one that's just right. And that's essentially what we're trying to do here. So this idea of too many versus not enough threads can be more formally referred to as suboptimal versus detrimental parallelism. So if we say that we gain maximal performance benefits at an optimal thread count, anything more than that is too hot, as we're gaining unnecessary overhead, and anything below that is too cold, as there's opportunities to gain further benefits. So these two tables kind of, or examples, illustrate this idea. They show the effects of parallelism on application performance. So we ran two applications by varying the amount of parallelism. On the left, we can see that as we decrease the number of threads, decrease parallelism, we decreased pause times. Over here, it's listed as a scavenger average, which is what we refer to as a collector, but that's not important. So anyways, we decreased the pause times and we increased the performance scores of the application. So the optimal thread count is 4 there. It's not too interesting, but the example on the right is more interesting. Over here, we can see with 48 threads, we were too hot. We're gaining unnecessary overhead. With 4 threads, we're too cold. We still have opportunities to further gain benefits. And with 8 threads, we can say is the optimal sweet spot. We could also refer to that as the equilibrium point, where work is optimally distributed amongst the threads being used, and it's the correct number of threads to use based on the hardware resource availability. So with all that being said, we need something to solve these issues, and we know that it's not so straightforward, which leads us to adaptive threading. And as the name suggests, the idea with adaptive threading is to adapt to an unfavorable parallelism situation by tuning the thread count. So coming back to the Goldilocks example, adaptive threading is looking for that sweet spot by observing parallelism in different scenarios, just like Goldilocks is tasting to figure out the right amount. So if we illustrate the relationship between pause times and the number of threads being used, or the parallelism, we'd roughly see a pattern like this. So this shows kind of how we expect pause times to react as we vary parallelism. So as we increase the number of threads, we expect pause times to come down up until a certain point, after which each additional thread basically results in a net loss and results in pause times being unnecessarily rising unnecessarily. So essentially, so we can see that there's this inflection point or the minimum on the curve, and essentially adaptive threading is looking for this minimum on the curve and trying to figure out which x value or what's the number of threads that results in that. So this is not so simple to do. We need to take many things into consideration. For one, and most important, this optimal thread count or this minimum is not static. It's dynamic. It's always changing as the application runs, and that's pretty. So there's few reasons for that, right? Depending on the application state, it could be ramp up, steady state, or startup. This is going to be very different. The workload's changing. The object graph is changing. Allocation rates are changing. So there's many parameters which cause basically a translation of the curve on the plane. Also, we can have processes spinning up. We can have multiple VMs coming up on the machine. So hardware resource availability changes as well as the application is running. And we can't predict that. Like, we have no control over that. So at some point, it might be best to use all the available resources. Or at another point, it might be best to use a fraction of the total number of resources as more processors are spinning up on the machine. So adaptive threading needs to account for all of that, and it also needs to react correctly given anomalies and one-off observations. So there have been attempts. So this has been a known issue, like inefficient parallelism. And there have been attempts in the past to kind of deal with it, mainly through two ways. One is manually tuning, explicitly setting the thread count when we start up the JVM, which the user can do. And so if we compare that to adaptive threading, we can see that manual tuning is not actually very robust. For one, it's very machine and platform specific. So if we run our application somewhere else, it could actually be detrimental. And another thing is that it assumes that this optimal thread count is static, and just like we discussed, it's always changing. And the other way that we've kind of dealt with this traditionally is through looking at indicators and letting the GC estimate the number of threads by looking at the heap size, or always preemptively using a fraction of the total number of threads. And so the issue there is that we're not solving the issue. We're just trying to minimize the effects of inefficient parallelism. So the heap size might tell us how much work we have, but it doesn't really tell us much about how it can be divided amongst the threads. Or it doesn't really tell us how about the CPU hardware availability for the threads. So overall, what we can say is that adaptive threading is a superior solution. It's a systematic approach designed to identify detrimental and suboptimal scenarios, and determine the degree to which it's suboptimal, and kind of give a recommendation on how we should move, what the thread count should be moving forward to kind of reach that sweet spot. So as I mentioned before, the sweet spot is always changing. So adaptive threading is designed to dynamically adjust parallelism through a continuous process of reevaluating and readjusting the thread count. In terms of implementation, adaptive threading is essentially a set of models and heuristics that work together to kind of judge or observe parallelism and determine how inefficient it is and how it should be moving forward. So it does that mainly by looking at the number of threads that are being used and the resulting statistics from using those threads. So we're mainly looking at busy and stall times from using those threads. So busy and stall times are key. They're what drive adaptive threading. If we know the number of threads we used and we know the busy and stall times from using those threads, we should be able to figure out how efficient parallelism is. Just like with Goldilocks, she's able to tell how hot and how cold each one is by tasting it. Adaptive threading is able to observe and determine how efficient we are. So we don't explicitly measure hardware resource availability or the workload distribution. These measures actually implicitly hint at those. So let's break down busy and stall times. So busy time is pretty straightforward. It's any time that a thread is doing useful work, that's explicitly contributing to completing the cycle, like scanning objects, copying or marking objects. But stall times are more interesting, and they require closer consideration. So stall times are, we can say two. When explicitly the thread is idle and not being used, basically not doing any work. And two, when a thread is not doing useful work. So it's doing trivial work which doesn't explicitly contribute to completing the cycle. So the premise is that busy and stall times are correlated, and the number of threads utilized has a dependent. So the premise is that busy and stall times are correlated, and the number of threads has a dependency on. No, sorry. So busy and stall times have a dependency on the number of utilized threads, and they're correlated. So for example, if a thread quickly reaches a synchronization point, it waits there for long, as compared to the amount of time it was busy. We can say that this thread is most likely not useful. It probably didn't have much to do, so that's why it quickly reached the synchronization point. So we can say that the ratio between time a thread is busy and versus stalled indicates a lot in terms of parallelism efficiency for that thread. So coming back to the example of too many cooks in the kitchen, and that's creating chaos, we can kind of like translate that into, for the GC, to something like this. So this is a scenario of a synchronization scenario of 4 threads. So 4 threads being synchronized. And it shows some of the different times we consider stall versus busy. So over here, worker 3 is the first to reach the synchronization point. So it has this large stall there. Worker 2 and 4 follow shortly after. And then worker 1 is the last to reach the synchronization point. And it doesn't need to wait. It just needs to tell the other thread, hey, we reached the synchronization point. Let's all wake up. So the time that each thread is waiting, the time that the last thread takes to notify each thread, and the time that each thread takes to start up and do useful GC work are all considered stall. And these are times that we actually measure. So why are these important? It's well, if we had more threads, there would be more resume stall, there would be more notify stall, right? So we can say that the number of threads directly impacts these different stall times. So this is just one example of what we kind of look at for stall. We're also looking at things such as when a thread is idle and not doing any work at all and it's waiting for work, so that's also considered stall. Sorry, I think I missed to mention just some examples of stall. So some examples of stall include idle waiting for work, idle at a synchronization point like I just mentioned, waking up from idleness, notifying idle threads, and then pushing and popping onto like global lists, or acquiring a synchronization monitor. So these are all dependent on the number of threads we use, as they don't explicitly contribute to completing a GC cycle. So let's take a look at how we can use this information to kind of find that sweet spot. So coming back to this graph, we're looking for this inflection lowest point, as I mentioned before, and we're trying to figure out what thread count results in that. So more formally, we can say that we're trying to find or trying to calculate the minimum on a GC time function curve. So for that, we first need to come up with the GC time function. We need something that lets us project GC time for any arbitrary thread count, because we want to see which thread count is going to result in the minimum. And we need to kind of do it in a way where we can take a look at previously used threads and the resulting busy and stall time. So we have to model that relationship. So this time function that we came up with proved to be pretty good. It basically says that GC time is proportional to the number. GC time is proportional to the number of threads, proportional to busy time, and inversely proportional to stall times. So in plain English, what it's saying is that if we have n threads and we know the busy and stall times from using those n threads, then we should be able to figure out what the GC time is for m threads, for an arbitrary thread. So the model is essentially derived by setting this to 0, which finds the minimum on the curve, and solving for m, right? We want to figure out what thread count results in that minimum. So with some basic calculus and with some basic math, we can come up with some models. So I'm not going to go too much into detail here. I think that's kind of outside the scope of this talk. I welcome anyone to take a look at the GitHub issues around it, which really details this provides a lot of details about this. So basically, I think the only thing to take away from this is that we can figure out the optimal thread count by knowing the percent stall, or ratio between busy and stall times, and the number of threads that result in that. So we can kind of project that optimal thread count. We were basically using some experimental data with some heuristics, like weighted averaging and thread boosting heuristics, to kind of massage that the number. In terms of implementation, how it fits into the overall collection process. So adaptive threading basically kicks in after parallelism activity stops, so during post-collection, and takes a look at how many threads were just used, and aggregates the busy install times from using those threads, and kind of massages the data to kind of try to judge how efficient parallelism was and recommend what it should be moving forward. And if it realizes that we need to pull down the thread count or pull up the thread count, it will flag that. So the next time we come and parallelism kicks in, it will take a look at if adaptive threading flagged a thread count. And if it did, then it'll just dispatch those number of threads. So let's take a look at it in action. So this is just a matrix of inputs and outputs that I kind of extrapolated at a given point in time. So over here, if at this point in time, we used 12 threads and we had 85% stall, adaptive threading would actually pull down the thread count to 9. And then it would flag that, and the next time parallelism kicks in, it'd use 9 threads, and then adaptive threading would again take a look at the busy install times resulting from using 9 threads, and again try to evaluate and for the next cycle. And so it's a continuous, it's a feedback loop. So these graphs illustrate how adaptive threading works throughout the application. So in the graph on the top, we see for any given cycle, GC cycle, how many threads were used and the resulting percent stall, so the efficiency of that cycle from using those threads. So in the beginning, we don't have any previous information about parallelism. So we use all the available resources, which is 48 in this case. And then adaptive threading realizes, it says, hold up, our stall is way too high. Let's pull down. So it pulls down to 30, reevaluates, still realizes still too much. And then it continually adjusts but for 10 cycles to reach this like optimal thread count of 6 or 7. Sometimes it pulls it up because we can use more threads. So that translates to, so if you want to see how it looks like for pause times, we can take a look at the graph on the bottom. So these each cycle is correlated here. So over here we have the pause times. In the beginning, we can see pause times are high, and we can see the portion of stall and versus portion of busy. So in the orange color, we can see how long is considered stall. So we can see that as we pull down towards the optimal thread count, we kind of eliminate a lot of that stall that adaptive threading realizes. So we also want to see how adaptive threading would behave in a multi-VM scenario where hardware resources are being shared. So we ran 6 VMs on a clean system, once without adaptive threading and once with adaptive threading, to see how pause times would be affected. And as you can see here, VMs 1 and 4 were running the same workload, so we just averaged the results there. And then VMs 5 and 6 were running different workloads. Overall, we saw a 10% reduction in pause times. But I think the most evident over here was VM5, where we went from 14 millisecond average pauses to 6 milliseconds. So that's about like a 70% reduction in pause times. If you want to take a look at the thread distribution, what's happening under the hood for each of these scenarios, with VM 1 to 4, we can see that adaptive threading is, I'll just back up. This is a graph that shows the frequency of each thread count. So it's a distribution. For any given thread count, we can see how many collection use that thread count. So by default, we would attempt to use all 64. But over here with adaptive threading, we can see that we're kind of somewhere between 40 to 50. But a lot of collections do attempt to use all the resources. But the most interesting one, again, is this VM5, where we had the most reduction in pause times. Over here, we can see that we barely ever use all the available resources. We always... No, it's just the 5th VM that's running. It's just the, maybe I should clarify that, sorry. But yeah, it's using a fraction of the total number of threads. We can see it's using somewhere between 4 to 10. And we did, a total of 3 collection cycles used 64 threads. And that's probably the first cycle where we didn't have previous information. And then 2 other cycles where we attempted to use it again to see if it would work out. And we quickly realized that it's probably optimal to use a fraction of the available threads. And so this is for the 6th workload, VM6. Again, we can see that there's some cycles that use the total number of threads, but again, the distribution lies somewhere between 40 to 50 threads. So that brings us to the end of the talk. Thank you, guys. Again, this work is available and it was developed in Eclipse OMR and Eclipse OpenJ9. So if you want to take a look at implementation details or you guys are interested, please have a look in these repos. You can search up adaptive threading and it should come up. So thank you. Let's pass the mic first.
How can we enable adaptive threading?
So adaptive threading is enabled by default in the latest IBM Samru builds.
J9.
Yeah.
Okay.
OpenJ9 builds.
Sure. Thanks.
Yeah. So it's enabled by default. It showed pretty promising results, and we've had pretty good feedback about it. Okay. You're next. Yeah. Oh well, sorry. We'll just take this question, and then I'll pass the mic to you.
So you say you consider the stall and busy time of the GC threads for adaptive threading, but what about the application threads? Because if you run concurrent GC, you also like the number of GC threads also affects how many application threads run, and you want to maximize throughput of the application threads.
Right.
Do you also measure that and take it into account?
Yeah. So this is specifically for stop the world because we want to reduce those pauses. So with concurrent, when GC threads are running concurrently with the application, we don't have this issue with, but it's that during that stop the world pause that we want to minimize those pauses as much as possible. So this is not related to concurrent technology. Yeah.
And last question, do you also consider to take into account profiling data, like for example, how much it takes to load memory for memory loads? Because like GC usually trashes all the caches, right? Because it jumps in the memory all around. So it might be that fewer threads don't do so much cache trashing and are faster. You measure that as well, or only explicitly time?
Explicitly time, but we are aware that different types of stall have different dependency on. So different types of stalls have different dependency on the number of threads utilized. So, for example, synchronization stall and resume stall and notify stall are more of a function of the OS and the platform, whereas idle waiting for work stall is more a function of the workload distribution. So we are aware of that, and but in practical implementation, we just consider all of it as one.
Will the adaptive algorithm be backported to J9?
I'm not too sure about that. That's a good question.
The proprietary one.
I'm not too aware how our OpenJ9 code gets used in the J9, but that's a good question. I can look into it and get back to you. Sorry about that. Okay, so just back there.
So, if I got it right, I thought the busy stall time ratio that you considered optimal was still around 50%. Is that correct?
I think for this example that I showed,
or even worse?
Yeah, the thing is that again, as I mentioned, that stall times have a varying dependency depending on the type of stall. So it's not a perfect correlation because we're grouping together all these stalls, like stalls that are dependent on the OS and platform, and stall that's dependent on the workload distribution properties, right? And they react very differently as we change the number of threads. So we kind of have to find like a balance between the two, and
so from your experience with that, I mean, I still find that very frightening, and I think in normal application we'd probably see similar ratios if we would do the same kind of measuring that you do.
Right.
So from your experience, are there low-hanging fruits that other data structures also that could be used to optimize this ratio?
So some of it is based on experimental data, like what we found to be optimal based on running different workloads. So some of it is based on that. Like you can see in these models, there's some constants, right? Like X. And so that basically determines the overhead sensitivity or tolerance as we change the number of threads on stall. So this 50% that you mentioned, this X variable, this constant, can be increased, and where we have more sensitivity to stalls, and we can react more aggressively. But we don't want to be too aggressive, As I mentioned, there's anomalies, one-off observations, so we don't want to adjust too quickly. That's why over here, we can see that we gradually decrease, right? And we don't want to decrease too much at the same time because we might be missing something. So some of it is based on experimental, yes.
Okay, thank you.
Thank you for that great talk. I guess we are mainly memory bound or memory throughput bound on modern machines, not so much the CPU engine itself. So cache structure and bridges between memories, like between multiple sockets for CPUs and so are probably things to look at or to understand how well we utilize the bandwidth that's available.
Right.
So if the CPU waits for memory because of cache invalidation or because it's taken a wrong branch, a speculative branch, and that's wrong, something like that. How is that seen? Is that seen as busy or is that seen as idle? And have you looked at these things, how well they align with your formula?
So those are considered busy. Again, as I mentioned, stall time is more so looking at when a thread has nothing to do, basically it's idle, or when a thread is at a synchronization point stalled. So we're not looking at those. We're taking a more like high-level look at things rather than more getting into specifics and details at the lower level. So we want to take a more of a high-level view of just taking a look at busy times and how long the stall times. But like you mentioned, those things are harder to measure during GC times because I don't think we have the we don't have. That's just going to be slowing down GC if we're taking a look at all those things. But if we're idle waiting for work, we can take those timestamps easily. Or if we're waiting at a synchronization point, we could take those timestamps and measure that really easily without any overhead. But I think if we take a look at more specifics, we're slowing down GC by, we try to make GC do work as much fast as possible. So we want to minimize operations. Yeah.
Adaptive threading sounds quite complex at times. So if it's built in, it's great. But one key takeaway for me would be that never use all cores or that many threads as you have cores, especially when you have many cores, because this would be definitely a downside. So this can be, say, a manual setting to just say take half of it or say square times the things you have.
Right. So as I mentioned, that's been a traditional approach to always use the fraction of the total number of threads. And again, that's to minimize the effects of it. But at some points, when we have a lot of work, it might be best to use all the available. Like if you have 64 cores available, 64 hardware threads, it might be best to use all of those when we have a lot of work, when the heap's really large. So we can't really, and as I mentioned, GC work is operating in different contexts, different configurations, different machines, different workloads. So we can't assume these kind of things. We have to take more of a general approach. And but these kind of approaches have been taken. Like, right.
And then our experience is use as many threads as are available. If they are waiting for I/O,
Yeah.
to wait, then it's better than when other threads do reasonable work.
So you mentioned the VM1 and 4, 4, 5, and 6.
Yeah.
You were running some manual tests, I guess.
So these were, this is part of a performance suite that we have.
Yeah, okay, so you have a performance suite.
Yeah.
Are you running that performance suite on different, because VMs are like,
Oh, sorry.
the other person alluded to, in a VM you don't have 100% access to all the hardware because there's a hypervisor in the middle.
Right. Sorry, I should clarify. VMs means JVM in this case.
Okay,
So we have
so JVMs, okay.
Yeah. So
Good.
we have 6 JVMs started up on the system.
That's good to know. So
Yeah.
you were running this on a specific instruction set?
On bare metal, yeah.
Okay, bare metal, but one instruction set. Are you running this performance test on different instruction sets? I mean, IBM
Different
has,
platforms? Yeah. This is-
has a number of instruction sets like PowerPC, and then
Yeah.
you have like Intel x68 and
yeah,
stuff.
so this is tested across different platforms, and there's varying. The numbers are different, but we've seen that overall it's beneficial for our platforms.
Okay, so did you at any point in time publish that performance suite which you have?
So we do have internally we do have a performance team which takes a look at this. So this was handed off to them for them to do this more rigorous performance testing on the different platforms and the different things. But as developers, after developing it, we do some basic performance. But I don't think the numbers are published for that. But
Okay, so but you don't have like a scenario where you have like all of those, like you didn't publish all of those performance tests, so we wouldn't be able to run that on our hardware, for example, if we would like to.
right.
And like just check whether the numbers are exactly as
Right.
you measured.
Yeah, but I think for as application level, the best thing would be to run this against your workload with adaptive threading disabled and enabled, and see how that affects you, rather than these numbers, which is like might not match your workload. But generally, we've seen that it works good across the board with different workloads. But your application might show different results. So the best thing to do is to disable it, run, and then enable it. And then we took the decision to enable it by default because we saw across the board that it did help, and it didn't give any regressions. Yeah.
Okay, thank you.
Is the adaptive threading available across all the garbage collectors offered by the OpenJ9?
It's currently it's on the default GenCon.
Only
Scavenge,
default.
Yeah.
Mhm. Thank you.
But that's a planned work, and eventually I think we will roll it out to the different collectors.
Thank you.
Any other questions? All right. Thank you guys. So if I would be really helpful if you guys could rate the presentation. As I mentioned, it's my first one, so it can be nice to get feedback. All right. Thanks, guys.